Part 4 of Talk on the Riemann Hypothesis. I introduced the idea of Fourier analysis, which is to take an arbitrary graph or signal or data, basically, and express it as a sum of what are called sine waves, the simplest kind of up and down wave oscillation. Trouble is that Fourier, because these sine waves are functions that never get very big or very small, they don't go high or low, they're like this, they're much easier to create a signal of the same type than create a signal, for example, like this kind of thing. If I wanted a function that goes up, 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 up forever, it's very, very hard. It's not impossible to make that with the Fourier idea, but it's very hard to figure out how to do that with the Fourier idea. And Laplace had a variation of the Fourier idea. I'm not sure if he thought of it that way at the start. And it involved what are called exponential functions. Exponential functions are like when you say exponential growth, like they're the way compound interest grows, or bacteria in a dish if they had given enough food, or sometimes population grows exponentially. They can grow somewhat fast, really fast, kind of moderately fast. There's various variations on an exponential growth function, but they all grow as opposed to oscillate and wiggle. And it turns out that somewhat like the Fourier idea of figuring out what kinds of wiggliness do you need to make up like this white square wave function. You can think, if I've got an arbitrary function, something that's not one of these standard examples of exponential growth, can I compare it to these guys and get an idea of how to analyze the function? So the idea is to describe a function by comparing it to various rates of growth. I'm going to leave it vague at that point. And it turns out, the idea actually goes back to Euler, but Laplace has his name on it because he did a lot with it. Turns out, these aren't just similar ideas, they're really the same idea. And I want to explain a little bit about that because it brings up another wonderful topic. And that is the connection between Fourier and Laplace is through complex numbers. So let me just give you a very brief tour of the idea of complex numbers. The geometry of ordinary real numbers. Well, what do I mean by the geometry of numbers? I mean that if I have a number line, just the ordinary real number line, here's 0, here's 1, 2, 3, 4, minus 1, minus 2, minus 3. I should mention, if I'm going to discuss complex numbers, those can seem very scary, kind of a weird, non-real kind of number. Not too long ago, a few hundred years ago, negative numbers were thought of as spooky and non-real, and you should never mention them. But we know better now. We all get into debt. We understand negative numbers pretty quickly, hopefully. What I mean by the geometry of real numbers is that one of the things that real numbers do is it encodes scaling. That if I look at the number line, if I multiply any number like n, or let's say x, and I take 2 times x, what does that do? It takes 0 to 0. It takes 1 to 2. It takes 2 to 4. It takes 3 to 6. It takes minus 1 to minus 2, minus 2 to minus 4. It stretches or scales. It doubles the scales, the scale of things. It's sort of like a zooming in. We see that a lot in sort of computer applications. You can zoom in and out of things like Google Earth or something. But it's a very basic idea of scaling up by a certain amount. What about multiplying by a negative number? That has a rather interesting idea. Minus 1 times a number. That takes the original number line. Well, 0 still goes to 0, but 1 goes to minus 1. Minus 1 goes to 1. 2 goes to minus 2. Minus 2 goes to 2. It flips it. It flips the direction. Or another way to say it is that minus 1 multiplication corresponds to a 180-degree rotation. It's the only kind of rotation that makes sense on a line. You can't have a line If you're living entirely on this number line, you couldn't do a 90-degree rotation. It wouldn't make any sense. Although we'll see pretty soon, we will make it make sense for numbers. What about if I do this scaling? Let's go back to the doubling scaling operation. What if I did that repeatedly? What if I took the number line and I doubled everything? So let me just try. I'm not going to track the progress of everybody. I'm going to track the progress of 1. If I double it, I go to 2. I double it again, it goes to 4. I double it again, it goes to 8. And of course, everybody else is getting doubled at the same time. But let's just think about where 1 goes. So it goes 1, 2, 4, or that's 2 squared. And then 8 is 2 cubed. And then 16 is 2 to the 4th. Repeated scaling is exponents. And so exponential growth, remember I was saying that the Laplace's idea was to take these very basic kinds of growth functions, exponential growth, and use those to describe any function. Well, exponential growth is just repeated scaling. It's just repeated multiplication by the same number. It turns out that our old friend E that I mentioned a while ago, it turns out that's actually a better one to use than 2, but we can think about as 1, 2, 4, 8, 16. Somehow, and again, I'm just trying to give a sense of a vague sense of the connections here, is that there's a way to think of these exponential growth functions that Laplace was so interested in using as building blocks, and think of them as this is what happens when you repeatedly use the geometry of real numbers. What real numbers do, a big role they have, is scaling up and scaling down, multiplying to get bigger, dividing to get smaller, and if necessary, flip to negative, a very limited kind of rotation. Well, complex numbers. Let me give you a very brief definition of complex numbers. Probably heard of them a little bit. You introduce this magic number called an imaginary number called I, and with the amazing property that I squared is minus 1, or in other words, it's the square root of minus 1. This is not a number we had before. There is no real number, no ordinary kind of number squares to a negative number, much less minus 1. Not only do we introduce I, we allow ourselves to multiply, to make 5 times I, or minus 7 times I. And we even allow ourselves to add those to ordinary real numbers. So it's things like 3 plus 2i, minus 7 plus 5i, etc. At this level, it's what mathematicians love and what almost everybody else gets very, very confused by or disturbed by. It's purely formal. I'm just introducing new symbols and trusting that they'll be useful. Well, you don't just introduce the symbols, you have to introduce the rules for manipulating the symbols. Still, that seems a little dry, but we'll see why we do it in a second. How would you multiply these guys? Well, what you want to do is you don't want to totally reinvent the rules of algebra. We'd like for the distributive law to hold. This idea that I talked about before, that if I have two things, a sum times a sum, I'm going to multiply this times this, this times this, this times this, this times this. And so that's written out here. Okay, well, 3 times minus 7, that's not hard. It's minus 21. 3 times 5i, well, hopefully the i's not doing anything weird here. And I just say, well, if I have 5 i's, whatever those are like, 5 oranges, and then I have 3 groups of 5 oranges, I'm going to have 15 oranges. Well, okay, so let's write that as 15i. 2i times minus 7, well, hopefully the usual rules of algebra hold, and it'll be minus 14i. And then here, 2i times 5i. Well, let's group the real parts together. 2 times 5 is 10. I times I is I squared. And now here's where the special nature of I comes together. Ah, I squared. That's supposed to be minus 1. That's supposed to be the new feature of this guy. So I don't have to leave that as it is. I translate that into a minus 10. And now these guys are just ordinary real numbers. I'm going to group those together. Get minus 31. And these guys, I got 15 of something, and then minus 14 of the same kind of thing. Whatever that thing is, that should amount to just one of those things. 15i minus 14i should be I. And so there's an example of multiplying complex numbers. And any multiplication of complex numbers is very similar. You can now do it if you want for any kind of numbers. But what does that do geometrically? Okay, well, what we're going to do is we are going to put this into a geometrical form, and we're going to talk about what's called the complex plane. And so instead of just having a number line, with 0 and 1 and 2 and -1 and -2, we are going to have, we're going to put I claim it makes sense to put I up here, and minus I down here, and 2I here, and minus 2I here. And then what about all those combinations? Well, let's see. 2 plus I, what we're going to do is we're going to say if it's 2 real parts and 1 imaginary part, we're going to put it over here. That's 2 reals and 1 imaginary, so we're going to call that 2 plus I. And so, for example, 3 minus 2I would be right here. Okay, so that's a kind of a funky way to introduce geometry into this. Does it make sense? Is it useful? You bet it is. What I'm going to do is, instead of repeatedly multiplying by 2, like I was talking about with the number line and talking about the geometry of real numbers, I'm going to repeatedly multiply by I. So I times 1, I'm going to start with 1 and I'm going to multiply by I. That's going to be I, that's up here. I times I, okay, so that's another factor of I. Well, that, by definition, that's minus 1. I times minus 1, I'm going to another multiple of I. Oh, that's going to be minus I. And I times minus I, ooh, that's a tricky one. But let's see. I times I is I squared is minus 1. Another minus, you get back to 1. So let's see what happened. I started with 1 and I repeatedly multiplied by I. Every time I rotated 90 degrees and got back to where I started after 4 times. What about I times 2 plus I? Okay. I times 2, let's look at the algebra here and then we'll look at the picture. I times 2 plus I is 2I plus I squared, I times I. Oh, I squared is another name for minus 1. Minus 1 plus 2I. Where is that? That is minus 1 plus 2I. It's here. If I look at this and this, that's a 90-degree rotation. These guys are the same distance from the origin, but I've rotated by 90 degrees. So again, multiplying by I was a 90-degree rotation. One more example. If I start out with minus 1 minus I, that's down here, and I multiply it by I, just using these formal rules of algebra, I get minus I squared, but minus I squared, cleverly enough, was plus 1. I get 1 minus I. That's 1 minus I. And again, it's a 90-degree rotation. And you can show that this always works, that multiplication by I is always a 90-degree rotation. And so complex algebra encodes rotation, not just 180, but in fact, and not just 90. In fact, you can encode any kind of rotation you want with complex numbers. And so the algebra of complex numbers, just this one simple rule, I squared is minus 1, it turns out that you can leverage that into a way to encode any kind of rotation as well as scaling. That's a much more sophisticated kind of geometry, and it still is just coming from what are really very simple algebraic rules. Unfamiliar and a tiny bit unfamiliar, but really simple algebraic rules. So remember that if I repeatedly multiply by 2, and I look at powers with real numbers, you get exponential functions. Turns out that when I repeatedly multiply with I, when I do the same kind of repeatedly multiplication of putting I in an exponent, for example, then it turns out I get rotation. This is a utterly incredible formula due to Euler that I don't want to explain completely, but it says cosines and sines, which have to do with oscillation. Remember, cosine and sine were these kinds of waves, the red waves. Those have to do with oscillation. Oscillation has a deep connection with rotating in a circle. If I look at something rotating in a circle, for example, all right, let's draw it here. Oop, I'm running out of my paper. Okay, here we go. If I draw something rotating in a circle, I'm just going to look at this rotating. I'm going to see if you can see my finger. Okay, see if I look to my pen. Pay attention only to how high it is, not to how far left or right it is. That's going up, down, up, down. It turns out that, if I just traced out the up-down behavior, it would exactly be a sine wave. And so rotation has to do with these fancy waves, or these very nice waves called a sine wave. And it turns out that the way to express that in a formula again, this is one of those formulas that I figured I had to write down, even though I didn't want to explain completely, is that the two fundamental sine wave pictures, which are called sine and cosine, you put those together with complex numbers, it turns out that's the same as repeated rotation. An example of that is probably even an even more famous formula, is that e to the I pi equals minus 1. Combines some of the absolute most important numbers in mathematics. E, which we've got a hint of its importance before, pi, which has to do with circles, I, which we now see has something to do with rotation. It says, what this says geometrically, I know it's not obvious, it says that rotating by half a circle, turns out that pi exactly gives you half a circle's worth of rotation. It's the same as flipping minus 1. So I want to understand this as a geometric statement. It's just the statement that a very special case of rotation is that if I rotate, I rotate, I rotate, I rotate, I rotate, if I do exactly 180 degrees of rotation, which it turns out corresponds to pi worth of rotation in a certain system, that corresponds to just taking like the number 1 and turning it into minus 1, or the number 2, plus 2, and turning it into minus 2. Very famous formula, and it has a geometric interpretation. So if you ever see this, I know I haven't given you any of the details, but if you ever see this formula, you want to maybe remember that it looks like an algebra formula, but the way to really make sense of it is that actually there's a geometrical meaning. It says rotating by a half circle is the same as multiplying by minus 1. So what I want to get out of this is simply, again, one of these vague connections, that complex algebra, and especially doing exponents with complex numbers, turns out to be, that encodes rotation. And especially it encodes like sort of repeating rotations over and over again. And so what does that have to do with the Laplace and Fourier story? It turns out that, as I said, the kinds of functions we wanted to model, let me go back to those. The kinds of functions we wanted to model were like this. They were like the Chebyshev psi function. That is not a function that looks like it's oscillating in any way. Well, maybe the little bumps up and down above, but the fundamental thing that this function is doing is it's growing. That's not something that looks like this. And so you wouldn't think that wave behavior would actually make much sense to describe that. Laplace comes along and says, oh, that's growth. I can understand growing functions by comparing them to standard examples of growing functions called exponential functions. Things like 1, 2, 4, 8, 16. Fourier, still though, Fourier is an incredibly powerful theory. And in some ways it's prettier than the Laplace theory. And the beautiful thing is if you bring complex numbers into it, you can pretend they're basically the same theory. If you look at Laplace and you allow complex numbers into the picture, it turns out it becomes Fourier, or really it's a synthesis of the two called Fourier and Laplace. So amazingly enough, there's a way to understand functions that grow by sort of pretending that they're really oscillating, and that involves putting I into this, putting complex numbers. So here's the idea so far as we have it. You start with some function f, some sort of picture of growth, like, for example, the prime counting functions. You apply this amazing Fourier-Laplace idea, which is substantial to learn how to do, but you can do it. What you get is something that gives you a map of the behavior of this function in the complex plane. Let me see if I can, some paper. Here's the complex plane, and it gives me a map with certain special locations. Maybe 2i is special, or maybe 2 plus I is special, or maybe 0.75 minus 0.9i. Turns out that it identifies certain very special points in the complex plane based on the kinds of growth and oscillation of f. It's a very weird and clever way to take a function and identify how fast is it growing. Is it a combination of different kinds of growth? Does it also have some oscillation at the same time, some wiggles? How fast are the wiggles? How big are the wiggles? That kind of stuff is encoded in a very clever way in a map of the complex plane, just various dots basically on the complex plane. These special points are called poles and zeros in the complex plane. And it then turns out, another part of it that I'm not going to explain, I don't think, at all, is that you can combine two other ideas that don't seem to be related: complex numbers and calculus. I told you how complex numbers come from algebra, and then told you a little bit about how they really encode geometry. Well, it turns out combining them with calculus is an amazingly powerful thing to do. So you can do that with any function, and it's a very useful thing to do. Could we do it for these functions like the prime counter or the Chebyshev prime counter? This story that I've been sort of trying to work up to in the last couple parts is a lot of why the Riemann hypothesis, if you actually read a description of what the Riemann hypothesis technically says, it doesn't seem to say anything to do with prime numbers. It's because of this rather intricate chain of ideas that we start out with something very simple, counting primes. This stair-step kind of function that we see here, a prime counter. And instead of talking about the prime counting function, the Riemann hypothesis seems to say something about this weird thing about the complex plane and some function and poles and zeros. What the heck does that have to do with anything? It's because of this kind of story and these amazing connections between growth and oscillation, scaling and rotation. And then the question is, maybe this is a totally useless thing to do. Maybe we're taking something that's already hard to understand, like the prime counting, and just making it into an even more complicated guy. Yes, we have some techniques from combining complex numbers and calculus, but maybe it's just a bad idea. Turns out, and I'll do this in the next section, turns out there's an amazing connection, that's the word, between Laplace, that Laplace idea of how to understand things in terms of their growth, and the zeta function. And we already knew that that had some pretty special connections with primes. And we'll do that in the next part.